Hello and welcome once again for another ES340 video. This is day 18 example problem 2. So the differential of pressure obtained from a certain equation of state. Remember, the equation of state has some kind of form that looks very similar to P equal to something over V, right? It could be V minus something as well, right? But it looks something like that form. So the pressure, we can solve it for the pressure. And the differential form of this is given by one of the following equations. And secondly, determine the equation of state. So the first thing is to determine which of these two it must be. And then the second part is determining actually what the equation is. Okay, so this is going to be a good example of how to do this. Now I'm going to remind you that it probably didn't occur to you why this was important at the time we were doing it, which is why I chose this problem so that we can actually work our way through. But exact differentials can be written as follows, and we'll actually put this in the same form, or we'll get this in the proper form in using dp and such in a moment. But this is what an exact differential looks like. If you recall, and then we called this term m equal to d z dx y, and we called n d z d y holding x constant, right? So we actually can see that both of these are in some form like that. I have, in this case, this is indicating, both of these equations are indicating that my pressure is a function of volume and temperature, right? Which we already know, that's true anyways, but that's what this is indicating, much like this was indicating that z is a function of x and y, right? Okay, so we can see that we can map these two things back to each other. And so what that implies to us then is that for the first equation, we have, I want to make one more detail, the test for exactness, right? I mentioned this in the lecture, but it's good to recall what that was. If we take the derivative of m with respect to y, in that case holding x constant, it should be equal to taking the derivative of n with respect to x holding y constant. Okay, so this is what we're working with. So first we should identify in these cases what n and m are. Then we can work our way through and do the test for exactness. And if it's not exact, then we cannot write that equation in terms of p of v and t, which obviously is a problem. So we'll be, as we work through this, we'll see that one of these we can reject and the other we cannot. So let's actually do that. Equation 1, we'll choose m to be equal to 2v minus b over rt. And we will choose n, right, because this is our exact differential, rather than partial. And here, obviously, then n has to be v minus b squared over rt squared. Okay, so now look at what we would have to do here, relating back to x and y. M is equal to d z dx holding y constant, right? So in this case, m is related to the volume, and n is related to the temperature. Okay, so what we're going to do then is we are going to take the derivative of m with respect to t, right? Because that's the opposite variable. Notice that when we do this, the variable that it was related to, we take the partial derivative with the opposite variable, right? When we do the test for exactness. So instead of x, we use y. M was related to v, so now we're going to take the partial with respect to t in that case, holding v constant, okay? So we're going to hold v constant here and take the partial derivative of this with respect to t, which since m is equal to 2, I'll rewrite this. I'm going to rewrite this over here that m is equal to 2 times v minus b times divided by r times t to the minus 1, right? That's going to be useful for us. So obviously the minus 1, when I take the derivative, the minus 1 is going to come over, and it's going to become to the minus 2 power, which I'll rewrite. So this becomes minus, because of the minus 1 coming down when I take the derivative, 2 times v minus b over rt squared, okay, because of the fact that it became minus 2. And then similarly, we're going to take dn now with respect to v, holding t constant. So n was equal to v minus b squared over rt squared. So we're holding t constant here, so the over rt squared is not going to change. And what we're going to be left with is, well, if I pull that 2 down, when I take the derivative, I get 2 times v minus b over rt squared. And now the question is, we say the test for exactness says that these two should be equal to each other. So this, the question is dm dt holding v constant equal to dn dv holding t constant? And the answer is no, right? Because I have a minus sign here and a positive here, right? So because of that, thus this cannot be written as P of Vt. So this cannot represent an equation of state. Okay, so this cannot represent an equation of state when it's written in this form. So the second one then, which I already hinted at before, we're going to find that in fact it can be written as an equation of state, and then we'll find the equation of state. Okay, so for 2, first thing is we're going to set m equal to minus rt over v minus b squared. And n is equal to, and again, m is going to be related to the volume of the specific volume, and n is going to be related to the temperature. But then n will be equal to, in this case, r over v minus b. Okay, so now what do we need to do? Well, similar thing. We have to take the partial derivative of m with respect to t, right, holding v constant. So holding v constant, well, that's just going to mean that I'm going to get something with a v minus b squared in the denominator. And I'm taking this with respect to t, so I get minus r over v minus b squared. Now, dn dv, holding t constant, well, there's no t obviously in this anyway, so that doesn't matter. And that's going to be equal to, well, again, I'm going to write this as n. N is equal to r times v minus b to the minus 1. So obviously, when I take the derivative, the minus 1 is going to come out front, so it's going to become minus r. And then it's going to be v minus b to the minus 2 power. So because I took those two derivatives, now I have this, and we can see that is dm dt equal to dn dv, and the answer is yes. So we can find an equation of state. So we rejected the equation of state for the first one. For the first equation, that is not an equation of state, but the second one is an equation of state using the test for exactness. Okay, so this is how we do the test for exactness. Now, the second part of this is finding the equation of state, because we know that this is an equation of state. So I'm going to rewrite this then as dp. Well, that's going to be equal to dp dv, right? Because that's exactly what m was dp dv, going back up to this thing, mapping it back to the z part. We know that m, I should write this actually out, is equal to dp dv holding t constant. And then n is going to be, of course, then dp obviously these are all partials, dt holding v constant. Okay, and going off of what we saw before, we knew that m up here was equal to minus rt v minus b squared. So that means that dp dv holding t constant must be equal to that minus r t over v minus b squared. And dp dt holding v constant must be equal to what we called n, which was r over v minus b. Okay, so that's what we have here. we can differentiate, or I mean, we can then, now this part might not be as familiar to you because I don't think you probably haven't taken like an initial course in in partial differential equations, so you might not know how this works out. So I'll just tell you how this works out. I can actually integrate. I'll integrate this equation. Why? Because it's going to be the easier one to integrate. Is why. Just not that you can't integrate the other one, but this one ends up being easier because there's no t in it, so it's going to obviously make an easy integration when you do the integral with respect to t. So basically, the idea here is I can notice that I'm holding v constant, and that's going to be a key part of this. But I can take this dp and set it equal to the integral of r over v minus b with respect to t. But the problem is that, again, this is holding v constant, so actually when I take this integral, the first part should look familiar, is that we get p is equal to r times t over v minus b, right? That part was simple, but the second part is now that I have to add on, instead of a constant, it's actually going to be a function because it's related to the volume here. So I end up with getting a function related to the volume. If I'd done it on this side, the function would have been related to the temperature, right? Because I'm holding temperature constant, but I didn't do that. Okay, so then what ends up happening is this is some arbitrary function of the volume, but it's nice. The nice part of it is it's only a function of the volume, not of the temperature. So that will help us here. So then when I insert this basically into the I can insert this now to the second equation, because I actually do want to get this in terms of t, right? Now I'm going to go to the other side. I'm going to say dp with respect, so dp with respect to v, holding t constant, must be equal to, right, because that's what this equation says, must be equal to RT over v minus b squared. Okay, so now what I can do is I can insert this into the equation. So if I take the partial derivative of this with respect to v, again, what I should find is RT times v minus b. I'm going to take the derivative of that, dp dv. That's to the minus 1, right? That's going to be equal to, when I take the derivative, the minus 1 is going to come out here. It's going to become minus 2. So this is going to be r minus rt over v minus b all squared. And then the derivative of the second part here is going to be, so plus the derivative of f with respect to v. Okay, right, because I'm taking the derivative with respect to v, right? So the derivative of that function, and then I'm going to want to know what that function is equal to. Well, from this expression up here, this must be equal to minus RT over v minus b squared, right? So now I can add this term over. So what this means is that this is the full derivative now. df dv is equal to 0. If I add that over, notice that this term and this term are equal to each other. So when I add that term over, this goes to 0. So what does that mean? This means that that I have f of v is equal to some constant. Right? Why? Because if that's the only kind of thing that I could take the derivative of it and get 0, right? Constants are the only things that I can write and get it to 0. That I can take the derivative of and get it to 0. So what this means is my equation of state P is equal to RT over V minus B, which we saw up here, plus some constant, which maybe we'll call capital C, why not? Plus some constant. Okay, so that's going to end up being my equation of state in this particular scenario. So that's the basic process. First you have to check, as we did here, and I think that this process should be pretty clear, test for exactness and determine if it even possibly could be an equation of state, right? So if it fails the exactness test, it can't be an equation. The expression can't be an equation of state. And then the second part is taking these and picking the easiest path forward. In this case, the easiest path forward was to integrate this one with respect to t, right? This one would have been, we could have gone the other route and integrated this equation first, but as I said, that would have been a little bit more complicated, and we would have ended up at the same path anyways. And then substituting that back into the other equation, because it has to satisfy, the equation of state has to satisfy both of those equations, right? It has to satisfy both this one and this one. Both of them have to be satisfied. So you have to do it just like you would do any other multi, if you're doing linear algebra type problem where you have to solve out two equations with two unknowns, same kind of process as here. Okay? That's all that I have for this video. Hope to see you again soon.